Hello, how you doing? This is problem 7 from your Even More Force and Acceleration worksheet. Um, a half-kilogram cart is on a ramp inclined at 20 degrees. The cart is tied to a 15-gram mass that hangs over a massless, frictionless pulley at the end of the ramp. Friction between the cart and the ramp keeps the system at rest. A. What is the force of friction between the cart and the ramp? All right. So I'm going to call this system A. Whoops. Yeah, there we go. I'm going to call this system B. Okay. So for system A, I have weight, I have normal, and I'm going to exaggerate my angle a little bit. And then I have tension perpendicular to normal. And friction, as we learned in class today, is actually going up the ramp. Okay. Now, if you put friction in the wrong direction, you'll just get a negative number. Okay? And if you get a negative number, you'll know that your friction is in the incorrect direction. But I'm going to show you the correct direction now. So these vectors need to add to 0. So I'll go ahead and add these vectors up. Friction, tension, weight going down, and weight must add to normal. So normal, weight, tension, friction, right? And that's a 20-degree angle because my normal force has to be tilted the same amount that my ramp is tilted. So if the system's in equilibrium, this is weight of object A, then sine 20 degrees is going to be equal to friction plus tension over the weight of object A, right? And so friction plus tension has to equal the weight of object A times sine 20 degrees. Now, I prefer to solve these problems with angle theta, so that if you give me any angle, I could just solve it. So this is for any angle, not just a 20-degree angle. And if I want to know the friction is going to be the weight of object A sine 20 degrees minus my tension. Now I'll go over here, and I know that the weight of object B has to exactly equal the tension since there's no acceleration. Acceleration 0, so the forces for both systems must add to 0. Okay? So this means that my tension going up and my weight going down must be equal. And I know my weight in the problem. So I can just replace, so tension equals weight in magnitude. So I can take this and I can plug it in here since the system is at equilibrium. Since the system is not accelerating. So the weight of object A sine 20 degrees, sine theta, sorry. Sine theta, WA sine theta minus T. Okay. So now I got WA sine theta minus the weight of object B. Now I can make this look a little cuter. People use G for the gravity field of the Earth, 10 newtons per kilogram. They also use little g for the acceleration due to gravity, which is about 10 meters per second per second. Okay, so I can say that friction is the mass of object A times lowercase g times sine theta minus the mass of object B times g. And now I can factor out my g. So g mass of A sine theta minus the mass of object B. And this gives me a nice general equation for any angle, any masses, and any planet. And let's see here. If the mass that's hanging becomes very, very large, that would be mass of object B becomes very large. Our friction would have to be very, very large, right? If the angle of the ramp, theta, became 90 degrees, right? If this angle became 90 degrees, let's go back up to the picture really quick. If the angle were 90 degrees, what would happen then? The acceleration would be then. Well, sine of 90 degrees is 1. And if the masses were identical, right, and the angle was 90 degrees, then there would be no acceleration, right? Mass of A minus mass of B was 0. 0 times G is 0. So our friction would need to be 0 if we had the same masses and our theta were 90 degrees. So this equation seems to be correct. Anyway, let's do part B now. Part B is slightly different. It's the same situation generally, except now we have an acceleration, right? So let me copy this over. Let's copy this. Copy. Next page. Edit, paste. All right. And now what we're talking about is removing a little bit of the mass that's hanging, and the whole system should accelerate this way, right? So let's see here. That means that the system that's hanging, system B, I'll still call this system B and system A, the tension has to be greater than the weight of object B, right? And for the cart, you've got friction going up the ramp, you've got tension going up the ramp, you got weight going down, you got normal force perpendicular to the tension and the friction, right? So you got normal, you got friction, tension, and weight, right? So when I drew my vector addition, first let's get the easy one out of the way, right? I've got tension going up and weight of object B going down, right? And if I draw my net force vector, my sum of forces vector, that's magnitude MA, I can see that T, tension in the rope, is going to be the weight of object B plus the mass of object B times the acceleration of the system, okay? And now I can go over here. I can do my vector addition diagram for system A. I got friction. I got tension. Now I'm going to make these a little smaller. I think they're a little long. Right? I've got weight going down. And I think they're still too long. Let me start with the weight. It's easier. Weight going down. And then I got normal force going up at an angle, right? And then I'm going to draw my tension really small and my friction really small, because that's the only way I'm going to have a net force. Normal. So my net force has to start here and there. So it's going to be mass of object A times its acceleration. And this angle, you recall, the normal force has to tilt by 20 degrees, right? So sine 20 degrees, it's going to be tension plus friction plus mass of object A times acceleration. And all of that is going to be over the weight of object A, because this is object A here. Cool. All right, and now I can take this and substitute it here. Okay. So now we're talking about sine, and I'll tell you what, instead of making it 20 degrees, why don't I make it any angle, okay? Sine theta is going to be weight of object B plus mass of object B times acceleration plus my friction plus my mass of object A times acceleration. All of this is divided by the weight of object A, right? So now I'm just doing algebra. Wow, let's write weight of object A sine theta is equal to weight of object B plus mass of object B times A plus friction plus mass of object A times A, right? I'm gonna make this look cool. I think I want to group my accelerations together. So, because then I can solve for A. That's what part B is asking. And I know everything except my A. So let's say weight of object A sine theta, right? Has to be minus weight of object B minus my friction has to equal mass of object B times A plus mass of object A times A, right? All right. So let's see here. Well, if I could just solve this by factoring out A, mass of object B plus mass of object A, right? And then I could just rewrite this chunk. So I got all this, just rewrite it. Oh, that's nice. I can't rewrite it. Weight of object A sine theta minus weight of object B minus friction has to equal that. Divide both sides by this part, mass of object B plus mass of object A. Yeah. So I get A equals, now I'm going to rewrite all the stuff that's on the left side on the right side. Weight of object A sine theta minus weight of object B minus friction. All that is over mass of object B plus mass of object A. The only other thing I could think of doing is like, instead of writing weight of an object is equal to its mass times 10 newtons per kilogram. See, we use lowercase g to represent 10 newtons per kilogram, or 10 meters per second per second. That's what lowercase g means. It's the gravity field of the Earth with the acceleration due to gravity, which is the same number, and the units are equivalent. So I'll just make it look cute and say acceleration equals mass of object A times g sine theta minus mass of object B times g, right, minus friction. All this is over the mass of object B plus mass of object A, right? And then you can get really cute here and just be like, okay, I'll take out my g. And then I got, let's see, mass of object A sine theta, right, minus mass of object B minus friction. All that is over mass of object B plus mass of object A. So you can check your work with putting the numbers in. I'm pretty sure that's cool, because if the angle, if the ramp were to 90-degree angle, sine theta would be 1. Let's say the masses were the same, right? And we had a 90-degree angle. This would be a 90-degree angle. You know, you'd have mass of A, mass of B, right? And if the masses were the same, we wouldn't have any acceleration. 0 times g is 0. Our acceleration, it looks like our acceleration would be negative f. Well, our acceleration should be 0 in that case. Do we have friction in part B? Yeah, I think we do. Anyway, part C. If the masses get really large, if you have infinite masses, very large masses here, the acceleration should be very small, right? And if mass A gets very large, that's the cart, then the acceleration should be very large. That sort of makes sense. Anyway, let's do part C now. I'm just going to copy this over because I'm pretty sure this is good. Part C is asking me to change some things. So let's see if I could do that. Copy this fool over. Whoops. There we go. All right, let's see if I can do it. Grouping, group, and I'll copy it. And I'll go to the next page, and I'll paste it. And I also want to copy the problem over. Whoops, there we go. See if I can do this. Okay, copy that. Okay, that looks pretty nice. I'll move this down. Okay, so if the original masses are used, but the angle is changed to 30 degrees, and the surface is frictionless, well, the only thing I have to do is take out friction, and this equation should work for part C. Because it says the surface is frictionless right there. So I'm done already. That's why I like to solve things in general, rather than plug numbers in. And now it actually makes sense, where if we didn't have friction, right, if this angle were 90 degrees, right, mass of A, mass of B, let's say this angle were 90 degrees, they were the same exact mass, right? Well, sine of 90 degrees is 1. MA minus MB would then be 0. 0 times G would be 0. So we would get 0 acceleration if these masses were the same. And that would make perfect sense because our system would be in equilibrium. If these objects both had the same weight, the system would have to be in equilibrium. And then another possibility here is if we have 0 degree angle. So that's a flat ramp like this. That's like a table, right? And there's the block, object A, object B, right? If we had 0 degree angle, horizontal surface, this is supposed to be a smooth curve, sorry. That would make this term here 0, and we would get our acceleration being equal to the mass of object B, G, and it would be negative, right? So we get MBG, so basically the weight of object B, and that would be the only force pulling on this entire system, the only unbalanced force pulling. So it would be that force and these two masses would be the total mass of the system. So that makes perfect sense. You would have the weight of object B being bigger than the tension, right? And in this case, the tension would be your only unbalanced force on this object, A. So I wonder how we could get an acceleration of g here. How could we make this whole term equal to 0? Maybe at 45 degrees? No. Well, if we have a 90-degree angle and how do we make that whole thing equal to 1? How does mass of A sine theta minus mass of B, how's that going to equal to 1? Well, not quite sure yet. I got to think about it. Anyway, hope you liked it. Hope it helps you understand. I'm going to erase the stuff that I don't want to mess you up. I don't want to confuse you. I think we're good here. Hope you enjoyed it, and have a good day.